You get it? Okay, thanks. I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray that you help us to wrap up our thinking for the final exam. And we thank you for semester and all your many blessings to us this year, Lord. In your name I pray. Amen. Okay, well, certainly we don't need to look at this. Ugh. Not yet, anyway. So final exam, I think I sent you guys an announcement already, but of course we're having our Calculus 2 final in here on Tuesday, if I remember right. Let's see here. Tuesday, 3:30 to 5:30. Yeah, so right in here. So yeah, not the 6 to 8, but the 3:30 to 5:30. So, I mean, I could make a 4-hour final. But I think we'll have 2-hour final, so 2 hours should suffice. All right. Where was I? Let's look at the, oh, goodness gracious. What's all this stuff? So here's the solution to that test you guys took. When was that? Tuesday, this week, right? It seems like forever ago. I think by and large, you guys did pretty well. Not everybody's where they need to be yet, but we still have like a long time till the final, so it's cool. You need to work on this material. I mean, there is still hope for everyone. Of course, statistics are against you, but forget statistics. We don't like those. Let's see here. See, I never give advice much on the basis of statistics. I mostly give advice on the basis of possibilities. So, see here. Let me focus. I don't multitask very well. There you go. One for you. Let's see here. Becky. That's yours. So what's your name again?
Park.
Oh, there you are.
And I get Sijin's.
Oh, you want Sijin's too? Okay, thank you. Excellent. Mr. Anderson? Oh, curses. Mr. Wynn? Okay. Micah while I'm back here. Sutton? How'd you get... So, many of you are about to take Calculus 3, am I right? Matthew, Grant. While we're at it, Grant. Paul. So, you guys had a lot of trouble on the, here you go. This is quiz 13. Yeah, a lot of trouble on the finding the standard angle. And so I don't know what to tell you about that. But the situation is that, I'm sorry, this is not the problem to talk about that. I'm getting ahead of myself. I think a lot of you had this right, actually. A fair number of you had this right, so it's not a worry. Any questions about problem 1? I'm actually talking about page 2. A lot of you had the acceleration right. Yay. You need to actually think through the fitting of the initial condition. You have to plug 0 in. Be careful. It's not just that whatever happens at 0 is what you add. If the thing you're looking at, the function, the antiderivative that you're looking at happened to be non-zero at 0, that can affect the calculation, right? Like here, e to the 0 is 1, and that means that I don't put 2, 1 as the thing I add. I end up having to put 1, 1. See, because this is 1, 0. So I need c plus 1, 0 equals to 2, 1. That forces me to have c as 1, 1, which puts a 1 here and a 1 here. And like popular wrong thing to do, just put a 2 here instead of 1, you know? It doesn't always work that way. And then you guys were doing a variety of interesting wrong anti-differentiation. I can only assume that that's just because it was this test. All of that will be out of your system by the final, because on the final we have much more interesting integration to do, right? So I'm optimistic that the mistakes that you guys made on this test on the integration will not occur if there's a corresponding problem on the final. Because I think your heart's not in studying integration right now, right? For this fourth test, you're mostly worried about what on earth is a parameterized curve and how do you work with polar coordinates and all that. And probably mentally you put integration on the back burner, right? So it's not too late to fix whatever went wrong there. Let's see here. And thank you guys. So any questions while I'm mulling about? All right, let me keep going through here. I think most of you got this one right, but I don't remember right off the top of my head. But you really should get this one right? I think we should all agree that this is a problem we can all do. It's important that you learn how to do it, because this is like pretty central thing that happens in Calc 3 a fair amount of different places. Like parameterizing a curve is something that's important to Calculus 3. So something you got to learn. And line segments are everywhere, so that's pretty common. Here, I think here my main complaint is you guys kind of stopped short. I said describe the curve, and you kind of just found the formula in X and Y. Didn't really explain what it was, or explain the wrong thing. But there was a lot of good effort there in problem 4. This is probably a significant, I would say, hole in your armor. This you need to fix. For those of you who got the wrong angle here, you need to get this out of your system. This is going to continue to take points away from you in math test and physics test unless you fix it. It's not just inverse tangent of 4 over 3. It's not inverse tangent of minus 4 over 3. Inverse tangent of like minus 4 over 3 is down here somewhere. Like, minus 3, 4. Something like this, right? So this is the standard angle. When you get inverse tangent of minus 4 over 3, it gives you a negative angle. It's this angle down here. This is the inverse tangent of 4 over 3. That's not the angle that you're looking for, right? So you have to take either you add this to pi, or you subtract inverse tangent of 4 over 3 from pi, and that gives you the angle. Just geometrically, it has to be that, right? It has to be an angle between 90 degrees and 180 degrees, or between pi over 2 and pi. Where is it geometrically? It's in quadrant 2. It should have that kind of angle. You have all seen this in previous classes, but you have not made it part of your core being. You need to find a place in your heart for this math, because it's important, and it will continue to take points away from you unless you fix it. I'm talking to like 80% of you. It's sobering. Fix this, please. Don't let me get you on this again, okay? Here, I don't know. There are some people who did some very weird things here, like very abstract. And I guess that just means that you didn't quite know what a centroid was or something. And that's just fine. Let's just set that aside. What you do, first of all, you got to calculate the arc length. Here, this is x and y both being non-negative, so that's like a quarter circle, right? So, I mean, I can do the integrate. The speed here is v if we use the parameterization r cosine theta, r sine theta. I was happy if you at least wrote that much down. Like I was like, yay, they know how to parameterize a circle. That's half the battle, right? And then speed is r in this case, and so the length is the integration of the speed over the parameter domain 0 to 2 pi over 2, which of course gives us pi r over 2. I would have been totally cool with you just telling me, hey, it's a quarter circle, so I'm going to take the circumference and divide by 4. Like that would have been totally legit here. But I don't think anybody did that. Maybe you did, I just missed it. But then to find the x coordinate of the centroid, x bar as it's called, we do 1 over the arc length times the integral of x ds. ds here is r d theta, and x is r cosine theta. Integrate this thing. And you guys need to be much more careful, not all of you, but some of you, about evaluation at the end of integration, right? Go to the trouble of integrating, but you're not really thinking through the evaluation carefully. Sine of pi over 2 is 1. And some of you just said that this was 0. Sine of pi is 0, sine of 2 pi is 0, sine of minus pi, sine of 3 pi, sine of 4 pi, sine of 5 pi. You get the idea. Sine of any integer multiple of pi is 0, but sine of pi over 2, well, that's 1. Sine of 90 degrees is 1. So this wrong thinking made some of you write 0 here, which is unfortunate, because you're just, you're snatching defeat out of the jaws of victory really here, or something like that. I mean, this is, like, if you got that far, you're so close to being right here. So that's why I didn't take off too many points for that kind of mistake there. But it is a serious issue, being careful and being precise with the end game of a definite integral, right? That's half the reason we're studying calculus, is to actually be able to calculate integrals for specific applied things, right? I mean, setting aside, of course, the larger goals of problem solving and deepening your ability to do mathematical analysis, actual calculation of integrals is one of our pet goals in here. Anyway, so this one is very similar, but we have integration of sine from 0 to pi over 2. The integral of sine is minus cosine. And this time, the 0 is giving you minus a minus cosine of 0 in the evaluation, which is 1. And of course, cosine of pi over 2 is 0. So I get... Now, of course, I would have been totally fine if you were like, hey, this is a quarter of a circle. By symmetry, you can see that the x and y coordinates of the centroid are equal. That's geometrically clear here that these had to match. So if you use that argument, I was fine with it. Any questions about this? I will tell you this, I am not giving you a note card for the final, right? So, what is one of the things you need to know for the final? Everything? Fair enough. But really, if you boil it down, there's really only a couple formulas for test 4 that you actually need to know. You need to know how to calculate arc length, right? You need to know how to calculate the surface area of a curve of revolution, and the centroid. I think that's pretty much it in terms of integral formulas. Area inside a polar curve, yeah. Very good. I'm thinking about the parametric stuff, but yes, the area, how to calculate area inside a polar curve. That should be ingrained by now, though. You kind of reflexively write 1/2 inner radius squared, outer radius squared minus inner radius squared, right? I bet you already know that. I bet that's not something you need to learn. Many of you already know that. So I don't think that's too much to add. And the thing is, I can't really give you a note card on the final, because then there's lots of basic integration questions I can't in good conscience ask if I give you a note card. Without the note card, it's totally legit for me to ask you integral of sine squared. It's a problem on the final. Right? With the note card, that question's dumb. So... I think, a lot of you got this, by and large, A and B, most of you guys got it right. Some of you kind of ignored the universe in which you're living, 0 to 2 pi. So you told me minus pi over 2. I don't think I even took off points because I just couldn't find it in my heart to take off points for that. But I did say 0 to pi over 2. So technically, these are the answers. And here, annoyingly, because I've included both 0 and 2 pi, technically there's 0, pi, and 2 pi, to be picky. But again, if you just gave me 0 or 2 pi, I let it slide. I'm just saying, I could have taken off points. But I didn't on that issue. So there's your times for horizontal or vertical tangents. Here's what they look like, roughly speaking. I've been having trouble getting my grid to show up on certain problems. Hopefully on the final, if I have some graphical questions, I'll actually have a grid that you can see. Some of my grids are like blue or something, and when I copy them on the department printer, they're just like gone. I don't think this one I had one, but there's some other problems where it's like that. You know, on the abstract algebra test I told you guys, I'm sorry, the lines are slanted. There were no lines. You're probably wondering what on earth I was talking about. In my copy, I had slanted lines, and then I somehow put the wrong page in and copied you guys the problem without lines for that the Gaussian integers module of the ideal. Sorry, I'll stop talking to an audience of one in here. Maybe I'm listening. It's two. So anyway, it's an ellipse, right? And of course, you can figure that out by actually finding its equation. I didn't ask you for that, though, did I? So I'm just informing you, hey, it's an ellipse, right? So if you didn't write this down, I didn't take off points. But if you had, you know, I'm pretty generous with it being lumpy and various other things, but it shouldn't be symmetric about the origin. It should be kind of down here. It shouldn't be over here somewhere. I mean, there are some things that will make me I can only bend so far before I break. Okay, so
I feel really sheepish about asking that, but can you show how to convert it to the 13th again?
oh sure, it's sine squared plus cosine squared is 1. So basically, when you've got cosine and sine in parametric formulas, the way to get rid of time is to look at sine squared plus cosine squared as 1. So just solve this for cosine and solve that for sine and plug it in. So this, like, solve this for cosine, I get x minus 3 over 2 equals cosine. I solve this for sine, I get y plus 1 over 3 equals sine.
Okay.
Square those, and you get the ellipse equation. So yeah, generically speaking, if I've got cosh and sinh, the way I eliminate time is cosh squared minus sinh squared is 1. If it's not cosine sine or cosh sinh, then I will sometimes just solve for t. I look for something that's common to all the equations to get rid of the t, generically speaking. A lot of you got this right. Woohoo! Some of you don't believe in bounds for the integral. Not cool. Some of you just wrote down square root of this stuff and no integral. Not cool. But generically speaking, good. So I've got this problem that I write down this, but then I put the dx up here and the dy down here. And I think that it's contagious apparently, because like 2 of you caught this disease as well. So I'm sorry about that. Because as you can see, I wrote this down, but I wrote it down so neatly, I couldn't give up on it. So I put an inverse up here to fix it, and then here again, and then here again. And then finally that's the answer. The minus is supposed to be in the denominator, because the minus appears with the x derivative, because the derivative of cosine is like minus sine, so like the negative is supposed to be in the denominator. But most of you had some idea of what you're supposed to do here. So generically speaking, pretty good here. Any questions? Let me go on. We have much more to cover today. Was there what?
Wait, go back.
So like, there's like maybe 2, 3, 4 of you who have my without the flipping. Yeah. Anyway. Area of surface of evolution. This ends up being an integral of cosh squared, which you should all be able to do either by converting it to exponentials or by using this lovely bit of hyperbolic trigonometry. Anyway, the answer is pi times 3 plus 1/2 sinh of 6 also known as pi times 3 plus 1/4 of e to the 6th minus 1/4 e to the minus 6. Yay. So again, the key here, of course, is starting off right, which is we're integrating 2 pi y times ds. The ds, of course, is the speed times dt here. Speed is actually cosh, because 1 plus sinh squared is cosh squared. Square root of cosh squared is cosh. Yep.
On my paper, you have a minus sign where it says 1 plus cosh 2t, like the third line.
Yeah.
Circle the positive, and you put a negative.
I put a minus there? Oh, that's whack.
Right there.
Oh, I was thinking you were doing sinh squared. So you took this 1 plus sinh squared and made it into a cosh squared, and then did the half angle identity in your head?
Yeah.
It's cool. But the point deduction remains because of that down there. Actually, this I didn't take F points over. It was actually this down here.
Okay.
Yeah. Okay, sorry. If this was the stack exchange, I would say your question was too localized. Sorry for those of you who know what I'm talking about. It's cool. I think there were about 10 of you in here who were not far from getting this. I was surprised. I thought maybe 5 of you would get this, because I think this problem's hard. So basically, you've got this circle is our 2 cosine theta. It's that circle right there. And then you've got the other one. I've lost its equation. It's a flower with 3 petals. It looks like this. Yee, like so. So basically, it's actually easier to see it if I just continue this back one cycle. So that gives me like the petal I'm interested in is this one. And then that gives me the next petal, and that's the final petal. At this point, I'm back where I started. So anyway. So in short, you integrate from minus pi over 6 to pi over 6. And I decided that I was just going to calculate the petal area and then remove it from the circle, because that's kind of a geometrically obvious thing to do here, right? Of course, you could also do 1/2 r out squared minus r in squared. Same animal. You just end up integrating cosine squared times 2 cosine squared divided by 2 over 0 to 2 pi, which gives you a pi, because the area of the circle is pi. So if you might have had like 1/2 of 2 cosine squared minus this thing. It ends up being the same thing. Anyway, after everything is said and done, a little bit of integration here, you get 2 pi over 3. So, all right, enough about this test. Do you guys have any questions? Though, let's go back to test 1. Yeah. Now, I plan to have office hours on reading day, and I'll send an announcement out about that. What's that?
I was wondering when Brandon was Monday.
Oh, Monday, yeah. I mean, shouldn't we read every day? Why are we setting aside a day for reading? Doesn't seem right. Seems like it's sending the wrong message to the students. Did your parents ever tell you that every day was Children's Day? I think at some point we all ask, why is there Mother's Day and Father's Day, but there's no Children's Day? And the canonical response is, every day is Children's Day. What are you talking about? It's true. You've heard this, yes. I think it's a past joke passed on by logic to parents everywhere. Cosine cubed. This is a gift. This is a totally expectable question. If you see this, you should say, it's an integral of an odd power of sine or cosine. I know what to do. You peel off the even part, leave one of the cosines or sines left over, and convert everything to either sine or cosine as appropriate through the cosine squared plus sine squared identity, right? So I peel off the even part, I convert it to 1 minus sine squared, I leave my cosine here, that is going to give me a w substitution. Any if you understand this problem, you should be able to do integral of cosine to the fifth, integral of sine cubed, integral of sine to the fifth, all of these. Anything where you have a net odd number of sines and cosines, you should be able to do through similar chicanery. Need to know integration by parts, obviously, right? I know it's been a while, but it matters. So, for example, basically the parentheses are your friends here. You do well to put in these brackets here, because otherwise we just have a propensity to drop negative signs where they're supposed to be, especially if it was supposed to be like a minus out here and it has to propagate through. We just have a tendency to forget of how many minus signs we have in a given term. So using some judiciously placed parentheses can be very helpful. That's what I do. Anyway, any questions about this? Anyway, I would just encourage you guys to review your integration by parts. You got to, generically speaking, if you're asked to integrate an inverse function, like inverse tangent, inverse sine, the natural log, anything that's an inverse function, probably the tool you want to use is integration by parts, right? So integration by parts is the natural weapon to use for the integral of an inverse function. So that's what you can use that silly Liate rule, kind of tells you this as well. But here u equals inverse tangent, dx is dv, so that gives me v equals to x. And of course, I also need to know how to differentiate inverse tangent, right? That's what we started with this semester. How to do those kind of derivatives, right? So derivative inverse tangent's 1 over x squared plus 1. Of course, u substitution is still important. I don't tend to test on u substitution by itself because this is Calc 2. We already did tested in u substitution on its lonesome in Calc 1 in here at Liberty, but you can hardly get away from u substitution, right? It's everywhere, right? I needed it here. I make a u equals to x squared plus 1. I guess I made it a w equals x squared plus 1 substitution. It's not because I have any particular love for W. I mean, I think he's an okay president, but whatever. Let's see here. I'm just excited because we're going to make America great again. What an awesome slogan. Sorry. It's fun. Next semester is going to be amazing. Like the political news for the next 4 years. It's going to be phenomenal. It's going to be good stuff. Like, comedians are finally funny again. Like, I haven't heard a single decent Obama joke for like the last 8 years. They can't bring it among themselves to make a decent Obama joke. There are jokes that could be made, but no one can make an Obama joke worth anything, as far as I've noticed. But I'm pretty sure that they're going to make some good Trump jokes in the next 8 years, 4 years, whatever. So, I mean, late night political humor, it's good again. It's exciting. That's right. That's my prediction.
Trump again.
Too early to call, but sorry. You guys, don't be. You see something like this. You got to dig in. You got to search your memory banks. You got to think about, how did we do that? Right? Notice that we've got x squared upstairs and downstairs. This is an improper fraction, right? So we got to do like long division, or you got to do an adding zero kind of trick in order to convert this to this. See, this is 2 minus 6 over x squared plus 3. That's what this is. When I do that, then I'm back in my happy place because I know how to integrate 2. And this is like an arctangent kind of integral, as you can see down here eventually. So. Let's see here, getting back. Partial fractions, of course, is important, right? Got to know your partial fractions. I think most of you are pretty good on that when we had this. I can't remember exactly, but I don't remember this class as being especially out to lunch with this. So I think there's good hope that you can study it again and try to internalize it. What's that?
Is this posted on Blackboard?
Oh, yeah. Yeah, it better be. If it's not, please let me know.
It is, and there's also a blank version
Oh, for your practicing? Yeah, I may not have posted a blank version of test 4 yet. I can do that too if you guys remind me. So generically speaking, the purpose of partial fractions was what? It's to take any rational function, rip it apart as a sum of basic rational functions. The reason we do that is we have a way to integrate all of the basic rational functions, either by a u substitution or by something like some kind of trig substitution for things like 1 over a quadratic. So this one here, completing the square is an important idea, but that doesn't help, not needed here, because if you complete the square, what happens? You get x minus 5 quantity squared minus 16, I think. So that minus tells me that it actually can be factored. So instead of completing the square, I factor instead. And so this partial fractions decomposition, super nice, because this I don't know how to integrate, but these are like taking candy from the proverbial baby. I would point out, as it should always be pointed out, this is a stupid thing. It is in fact very difficult to take candy from a baby if you've ever tried. This is very important life advice. Don't take candies from babies. It makes them very, very upset.
All you have to do is distract them with something else shiny.
You can't distract a baby from candy. That's crazy talk. It's impossible. No, you can't do it. It's just give up. I'd sooner fight a land war in Asia. Sorry, is that too obscure a reference? Let's see here. That's right. It's inconceivable. Let's see here. Calculate the area bounded by this curve. Well, this is an ellipse, right? And so, you got some sort of analytic geometry to do here. Area bounded by a curve, right? So we set it up, and then after all that's said and done, we've got to do some actual, trig substitution here. But after you go through the details, it's actually very satisfying. The answer, right? Pi AB. So, the point of this is not for you to memorize pi AB. So if I had put this problem on the final, and you write down pi AB, I mean, I'm happy that you studied, but I need to see the details. Okay. This is actually a pretty good problem that I can kind of separate some B and C students with this one sometimes. Dr. Sperano says I'm being too nice here because I told you to use trigonometric substitution. I told him that it didn't matter. This niceness wouldn't change my grading much. I stand by my belief. But I don't have to tell you to use trigonometric substitution here. You should have the idea to use trigonometric substitution here just the same, because it's got a radical, right? So anytime you see a radical, if it's got a square root, it's very likely trig substitution is a good choice, or possibly hyperbolic substitution, right? If I want you to use hyperbolic substitution, I'll probably say, please use hyperbolic substitution. I give you the freedom to always use it, pretty much. Unless, of course, I were to say what? Use a trig substitution, right? Yeah, so. But usually I forget to put these kind of blinders on you, and you can just use whatever method. I mean, in my heart, I want to say that it's totally reasonable to tell students, integrate this thing, right? And there might be a student who writes down, just thinks really hard and goes, sir, it's the natural log of the absolute value of the square root of x squared minus 2x plus 5 plus the quantity x minus 1 plus a constant. And then he will differentiate that and show me that it works. I mean, I have to give him credit. But pragmatically speaking, I would probably just thought you cheated. But I don't want to think you cheated. In principle, if you could guess the answer, it's, this is all systematic guessing at its core. Did you ever derive that the integral of sine is, minus cosine? Did we actually work out the Riemann sum and show you that it converges to sine for an arbitrary bound or whatever? No, we didn't do that. So we made an educated guess, which was, oh, what? Cosine, if you put a minus on it, you differentiate it, you get back sine, right? So it's the antiderivative. Did we derive that? No, we made an educated guess. So if your intuition allows you to make the educated guess of that, and then you prove to me that it works, you differentiate it, I would have to be a real jerk not to give you credit. But again, pragmatically speaking, I'll think you cheated. So I'm very torn about this issue. So anyway, I don't know. I'm not really worrying about an actual real student that exists. Like no one can write down integrals like that as far as I've ever met a person. But I can't deny that such a person could exist. At the start of Calculus 1, when I ask students to guess integrals, there's a vast diversity in talents. Some people can guess some pretty complicated stuff early on. It's fun to if you guys ever have the opportunity to teach high school calculus, you'll discover this yourself. Just spend an hour, find out what students can guess. It's fun. Before you teach them all these rules and techniques, see what people can guess. It's interesting. Now here I have given you so much guidance. Complete the square and make appropriate hyperbolic substitution. In some sense, I'm being very kind here, right? I can remove this sentence on the final and just say integrate that. Right? I might take off this guiding sentence and just ask you to integrate it. Yeah? Or I might be lazy and cut and paste. I don't know. Who knows? I can't say what I'll do tomorrow. Ask me. No, don't ask me tomorrow. I won't tell you. I will just give you vagaries. No one has asked me how many questions on the final yet. Shocking.
I think I asked like a week or
Oh, you asked a week ago. Oh, okay. And did I give you a very vague, non-specific answer?
so. It was like
22. Oh, see, I've graded like 3 tests since I gave you that answer. I think the current number of questions is at like 8. I'm tired of grading. I want a shorter final. Ooh, look at this. I will try to put at least one question on the final, which is stupidly difficult. Just to see if you can do it. Yeah? I try to always do this on my tests, guys. It's not just to be mean to you. It's because some of you will ask me for letters of recommendation later. It's very useful to me if you solve a problem that somebody only solves like every 10 years. Because then I can say in your letter, such and so forth solved this problem. I put it on there as a joke, but they actually solved it to the point I got it. So I had a student do that a few years ago. The Weierstrass did I show you guys the Weierstrass substitution in here?
Yeah.
I did, right? There was a semester I did not teach it. And I just put on the test nothing more than make the substitution t equals tangent x over 2. And he managed to use that to actually solve an integral. Like he discovered the whole, how it works, the relation between dx and the sine and the cosine substitution, all of that on his own, on the test, during the time pressure, and solved the problem to the point I solved it. And had the wherewithal to say, oh, at this point it's just partial fractions, so we're done. Like, that student, I was able to write a very good letter for, because he did this, right? So I try to do that, so I have some stories to tell about you guys. For the rest of you who don't get those problems, it doesn't hurt you, as long as you don't let it hurt you, right? You kind of have to have some common sense. If the problem is at the end of my test, and it looks like that, you know, you should try it when? When you've finished all the other stuff, right? Yeah. On the flip side, sometimes I make these really easy just to mess with you. So, you know, there should be some gamesmanship in tests, otherwise it's no fun. You disagree? And I disagree, it's fine. Oh my goodness. So anyway, that problem. What was test 2 about? It's been so long. Stuff. Seems safe to say. Differential equations. I thought that was a different class. We did that in here? You guys are like, ha ha ha. It's not that funny. So for differential equations, there are 2 main tools you need, right? Separation of variables which is just what it sounds like, right? And separation of variables problems are pretty awesome because if I ask a good separation of variables problem, I can like test a couple different integration techniques at the same time, right? For example, what if I was to ask you, dy dx is equal to, I don't know, x log x times y squared plus 4y plus 3. Then you'd get dy over y squared plus 4y plus 3 equals to x log x dx, right? Then, so we separate variables and then we integrate both sides, right? And the thing is, this one's like super fun because this you'd need to do partial fractions on, right? To figure that one out. And this one, you do integration by parts. And so it's pretty easy for me to come up with a differential equations question which simultaneously tests chapter 1 stuff, you know, which gives me less grading. Yep.
What was your UV on that integration by parts?
Oh. Yeah, I think I make exactly, so that's my v, my dv. So I get 1/2 x squared log x minus the integral of v du, which would be 1/2 x squared dx over x. Yeah. So it's not too bad, I don't think. There's something similar that's much more awful. Maybe if I put like x plus 1 here, bad things happen. Okay, let me stop thinking about how to make it worse. So separation of variables is important, right? You need to know that, have a clear understanding in your mind how to do that. And then the other technique for solving differential equations was the integrating factor method, right? If it has form dy dx plus py equals to q, we multiply by the integrating factor. That will allow us to do the reverse product rule, and we can solve it. Right? This was a non-obvious but standard technique that we covered in the class. If you don't know that yet, you need to learn it, right? Because without that technique, there's a large swath of problems you can't solve. There are things that if you don't know the integrating factor technique, you cannot solve them, a lot of them, by the separation of variables. Then the other main application we had here was the orthogonal trajectory concept. And I think what usually happens is it's kind of on the edge of what students study. So a lot of you don't really quite have enough time when you're studying this test to quite absorb what an orthogonal trajectory is. And so it slips through the cracks if you're studying, like a lot of people. And it's got a kind of scary name. It's an orthogonal trajectory. I don't know, I think that's part of the problem. Like if I could change the course title of advanced calculus to like easy and interesting calculus, past calculus 3, I think I'd get better number of people in there, right? Advanced calculus, not helping the course. It's a bad title. So maybe we should call them perpendicular trajectories or something. I don't know. All we're doing is we're taking the differential equation for the given curve. First of all, you got to find it if you're not given it. And then you just do the negative reciprocal of that formula, whatever it is, and that will give you solutions to this will give you the orthogonal trajectories. That's all there is to it. Right. So these do not have to be hard. There is something to learn and remember there, though, yeah? Implicit versus explicit. Implicit means you can give your answer as an equation, right? Explicit means you have to solve for y. If I don't say one way or the other, if I just say solve, it's up to you. You could leave it implicit or explicit. Those are the rules of the game in here, at least for me. Some other professors don't agree with me, and if they say solve, they probably want you to find explicit. But my understanding of differential equations is that the implicit viewpoint is more general, so I'll accept it as an answer. Of course, if I say explicit, then I actually want you to solve for y, right? But anyway, implicit just means it could be an equation like this one. And sometimes you can't solve for y, right? Like this, can you solve for y? I mean, I can't solve for y. Now here I said explicit, right? So I had to solve for y. We did talk about how to calculate limits. What was the main tools to our disposal? Extend n continuously, use L'Hopital's rule, right? That was the big thing we learned. And of course, before, you still have all of your favorite, previous ideas. Like if I look at 7n plus 13 over 2n plus 7, I should immediately be able to tell as n goes to infinity, that thing inside the log goes to 7/2. Right? You should have an intuition for that at this point. And the log being continuous, I can pass the limit inside the log, and then I get natural log of 7/2. Of course, that's natural log of 7 minus natural log of 2. We've talked about how you can use calculus to show things are increasing or decreasing, right? That's really a Calculus 1 topic, but I feel strongly about this being something you should know, so I revisit it in this course, right? We've spent a fair amount of time differentiating functions, showing they're positive or negative to prove that they're increasing or decreasing, right? So that's something I hope you picked up on. I hope you're able to, to use if you face a question like this. We haven't spent an awful lot of time. I probably have not spent enough time talking about recursion in here. I'm sorry for that. If it's something you liked and I didn't spend enough time on, that's my bad. But recursion is important, and here's a nice example of it. Squeeze rule is important, right? Did I say without using L'Hopital's rule here? Just because you guys, once you get L'Hopital's rule in your head, you got to use the L'Hopital rule. Like it's like a drug. You get a taste. And but no, this is a squeeze theorem problem. So there's also the indeterminate powers, right? You should review that if you're rusty on that. Yep.
So, you see how you said we have to use L'Hopital's rule, don't use L'Hopital's rule. So what if we don't know it any other way and we do use L'Hopital's rule? Will we get 0 points?
I would probably give you a point.
That's better than that.
I mean, yeah. I mean, I might just ask questions like, by any means necessary, what's the answer to this limit? Because that is easier for me to grade. Sorry. I hope you're noticing a theme. I'm tired of grading. Anyway, let me get to it here. Improper integrals, of course. You've got to be aware of how to do improper integrals. Basically, there's two kinds. The ones with infinity explicitly appearing in the bounds. The other ones are integrals of unbounded functions, like this one. We have to approach, endpoints that are misbehaving as appropriate with appropriate limits, or this one here. This means we take the limit as t goes to infinity of this definite integral, so forth. So we talked about those. We had a comparison theorem, which is super nice. Excuse me, because we could trade things that are just, I can't even express to you how much I don't want to integrate this function. I mean, no. Ugh. And then this, in contrast, yeah, we can integrate this thing all day long, right? Easy peasy. And so this is, in fact, a known integral. We know this converges. It's part of the proof of the P-series, right? Actually, we proved the P equals 4 series by showing that integral converged, and in retrospect, anyway. So there's this argument by comparison is super nice. Keep in mind, it is for functions which are positive. And what? They have to be positive decreasing functions, I think, if I remember right. Although in my heart, I feel like positive should be enough, but decreasing is needed somehow. Don't trust my heart. Let's see here. There's stupid people who always tell you to follow your heart. You should ignore those people. What's that? Yes, Jeremiah 17:9. That verse, it casts a long shadow over psychology. Like, the heart is desperately wicked above all things. Who can know it? We can, right here. We'll give you a degree in it. Sorry, I misbehave. I probably need counseling. Let's see here. Oh my goodness. I hope you realize by now, I hope as you go back and look at problem 1, it should sting you It should hurt you that you lost those points. You should want those points back. Those points could be yours. This question was very simple. I tell you the partial sum has formula 3 minus 1 over n. What is a series? It is the limit of the sequence of partial sums. Right? That's the definition of series. So, take the limit as n goes to infinity. 3. Yes, the series converges to 3. That is it. You guys, some of you did very complicated stuff here. No need. What would have been a more exciting question is for me to ask you what's the formula for a sub j given this. Could you do that? Can you find the formula for a sub j from the formula for the partial sum? If you take the difference in the nth partial sum and the n minus 1th partial sum, what should it give you? Think about it. You take the sum of the first 10 things and you subtract the first 9 things. What does it give you? Gives you the 10th thing being added. So you can do that for arbitrary n, just the same. Anyway, that's a kind of bizarro. Let me just go for a few more minutes here and I'll shut up. Sorry, going over a little bit. What's the likelihood I ask a question on the final that's the nth term test? I would say the odds are about 90%. It tells me a lot. If I give you a series, right, and you look at the term and you tell me the limit is 1, so it converges, that's your way of telling me I don't know what I'm doing. Because the only way, if this goes to something non-zero, that means it diverges, right? If this goes to 0, if the nth term goes to 0, it tells you nothing, right? So that's kind of like the first thing we learn, past the definition. And so it's a good question. And it doesn't have to be this one exactly, but there's tons of them, right? Ratio test is a big deal, right? Geometric series, if I was only allowed to ask you to learn 2 things about series, I would ask you to learn the geometric series and the ratio test. I think you get the most bang for your buck with those 2. What's that? Wait, what did you say? Root test. I don't. My heart's not in it. I don't know.
Ratio test and root test overlap.
Yeah, but geometric series is so very important. Now, past series, we have power series, right? You need to know your power series. What's the power series for exponential, sine, cosine, cosh, sinh? These should all be known to you, right? There's nice relations between those, so it's not like remembering 5 different things. It's really just like remembering maybe 2 or 3 things, and there's a nice web of interrelatedness there that you can exploit for your memory's sake. We have these interval of convergence problems, right? It's pretty good chance I ask you one of those on the final, honestly. It tells me a lot. And it's nice because it's got a ratio test in it, and then you got to check endpoints, right? So I get to test the numerical series as well as the power series all in one big sweeping question, which is really what we're after, is this understanding of the interval of convergence. That's the whole point of the convergence theory. And of course, this problem 6 is, I think a lot of you had a lot of trouble with it on the quiz. Most of you kind of came to terms with it on the test. Still, a few of you on the test still hadn't quite got it. So do try to think about this some more if you got that test question wrong. Try to come to an understanding of the idea here, basically, that if you have a point of convergence close to the center, you are forced to have all points closer than that point converging for the series. And if you have a point of divergence, you're forced to have all points larger than that distance away from the center diverging. And then anything in between that, it's ambiguous. So that allows you to find the largest and smallest, basically. Let me get through here. I'm almost done. There's the integrate and differentiate geometric series problems. These are important. How do you find power series for natural log 1 plus x? You differentiate it. You find the geometric series for 1 over 1 plus x, and then you integrate to get back to the power series for log 1 plus x. At least that's how I do it. I mean, you could use Taylor's theorem directly, but geometric series tricks for finding power series, very important idea. Of course, the actual Taylor's theorem is also important. Sometimes I just want you to use the Taylor series, and I will try to be more explicit about that, like this here. Find the first three terms in the Taylor series, Centroid did this for that. I would actually like to add the instructions by explicit differentiation. And maybe for another problem, I would say by substitution techniques, right? Like, find the first three terms in the Taylor series for exponential of x cubed. How would you do it? Just like this. See, you don't need, this is the first three terms in the Maclaurin series for e to the x cubed. I don't need to differentiate. I can just do a substitution for this problem. So it's rather different than that one in this sense that it allows this easy calculation, this substitution. Assuming you know the known Maclaurin series for the exponential, I hope you do. Of course, then we can use the power series to do integrations, like so. And anyway, I'm out of time, so I'm going to shut up. But I think we've covered pretty much everything. This is your life, Calculus 2, in an hour. So everyone who's here has a legitimate chance at passing the class. But you got to convince me that you know the basic stuff in these tests, right? So sweat the basic stuff first. Yeah.
For the Wednesday, final, where is that?
When was it? Wednesday?
The Wednesday.
What time was it I told you? Oh, that's Science Hall 142? Yeah. Some people Wednesday are taking it with me in here. I have another one that's here, like 3:30 to 5:30. So I have to check which time you're talking about. Certainly.
Problem 5 right here. I had 0.705 pi, and the answer was 2.214, which...
Oh, yeah. I give that back. Yeah. I just didn't see that for what it was.
Okay.
That's cool. I'm sorry. I just didn't.
Hey, no worries.
It didn't pop out at me. I'm ashamed. I should have seen that. Here, let me fix it. Let's see here.
And are these answers posted?
Not yet.
Not yet. Okay.
He's like, no cards for just one of the tests. Like, my professor gives us a note sheet for every single test. Like, what?
For which class?
It's another calc professor, a calc 2 professor that gives them a note sheet.
Here?
Yeah, he's new this semester.
Calc 2?
Yeah, the teacher's new. Calc 2.
Here.
Note sheet.
Here?
Test here.
Here, Calc 2 gives note sheet. What's the name of this professor? I'd like to know.
He's new.
Don't ruin it for these students.
Does he teach Calc 3?
Right? That's that class. I'm like so excited for the note card. I'm like, we can't get to the final, but at least one test with the note.
It's funny. So I took a point off for that? 4 points.
I think 2, because this one was wrong. So I'm assuming it's just 2 points.
Yeah, I took 2. You're right, 2 points. So that's 121, right?
Yeah.
There you go.
Thank you.
Pretty good. You too. Yeah, I should post that in Blackboard when I remember.
All right. Appreciate it.
Hopefully soonish. All right.
So you're really early Calc 3 next semester, right?
Yeah.
I think I had a slot, but I think I had one meeting with you.
You know this guy?
I know him.